Good morning, everyone. Welcome back. Thanks for watching the video. See that I only get a few views, so if you're watching, subscribe, tell your friends, so we can get some more guys on here watching these. I think that they're useful. Hopefully you do too. I hope you guys are all staying well. Hope you're not too bored, keeping yourselves busy, being productive, not just plain, and the additive property of inequalities. So first off, domain. This word domain comes from Latin dominus, meaning master. The domain in English normally means that's the area that you control. And when we talk about it in a mathematical context, it's going to have a similar meaning. This is the area that we can use a particular equation in. Let me give an example. So when you're doing a problem, it's not the case that any number is possible as an answer. For example, if you're doing one of these ratio problems and what you come out with at the end is that there are 34 and a half ducks and 22 and a quarter geese, that's probably not correct. You can't have a half a duck or a quarter of a goose. I suppose you can, but not in a live sense. Similarly, you can't have a negative number of certain things. If I want to know how many boats are on a lake, it can't be a negative number. It has to be a positive number. And again, it's probably going to have to be a whole number of boats unless somebody has taken their boat apart and put it on top of another boat, which is currently on the lake. So especially when we deal with things that have some connection to the real world, we're going to have to think about this question of domain, is what are my possible values here that I'm dealing with? So we saw in those examples, very commonly will be limited to positive numbers. Very commonly will also be limited to integers or whole numbers if we're talking about positive ones. So the formal definition of domain is the set of permissible values for your variables in an equation. And when we have an equation where there's a domain specified, we have to keep that in mind because other values are not going to be things that we can deal with. If we're talking about those boats on a lake, negative numbers are just going to be out of the question. The way that we write it, notice it's a set of values. So we write it using set notation, using the curly brackets, D for domain equals, and then the set there. Of course, if it's one of our other sets of real numbers, then we can use the symbols for those, the fancy R for real numbers, the fancy Z for the integers. We'll see a couple examples in a minute. The other topic here is the additive property of inequality. We had the additive property of equality before, which means that if you've got two things that are equal and you add the same thing to both sides, they're still going to be equal. Similarly, if you have two things that are unequal, so for example, if A is greater than B, if we add the same thing to both sides, they're still going to be unequal in the same way. A plus C is still greater than B plus C as long as A is greater than B, because we know that those C's are equal to each other. So just like we did with equalities, with equations, where adding the same thing to both sides is something we're allowed to do in algebra, similarly, we can do that also with inequalities. And that won't change the value. It won't change the solutions of that equation. So let's look at a couple of examples that use both of these. We're going to be graphing some inequalities here, but keeping in mind both our additive property of inequality and also this concept of domain. So notice for each of these inequalities, let me move here so you can get a better view. For each of these inequalities, I've also specified a domain for them. So the first one here, x is not greater than or equal to 3, and the domain is fancy R. Fancy R stands for the real numbers. So we're talking about anything positive or negative, rational, irrational, as long as it isn't an imaginary number, which, as I said, we're not going to deal with in this class. Then it's a possibility here. So we need real numbers that are not greater than or equal to 3. So the only thing left is real numbers that are less than 3. And once we figure out that this is actually less than 3, then it's simple enough to just put that open dot on the 3 and the arrow pointing to the left, indicating that it keeps going on forever in that direction. Now notice this continuous line here. I draw a continuous line because any of these values here, literally any real number less than 3, is going to be a solution here. real numbers are an option. They're a possibility here because that's our domain. For the next one, that's not going to be the case. Notice here we have x is greater than or equal to -1, but our domain is not the real numbers. Our domain is fancy z, the integers. So things that don't have a fraction or a decimal part to them, both positive and negative. So x is greater than or equal to -1. So -1 is an option. Okay, we can put a dot there because that's an option. What about 0? Okay, 0 is also an option. But notice I'm not going to draw a line here between the -1 and the 0, because by putting a line there, I would be saying that anything between the -1 and the 0 is also a possible answer here. But since I've specified in the domain that we're only talking about integers here, I can't draw that line. I'm just going to have to draw dots on each of the possible values here. Then with the understanding that this pattern is going to continue forever in that direction. All these values where x is greater than or equal to -1. So when we're dealing with integers or whole numbers or natural numbers, any of those where fractions and things are not a possibility, you're not going to draw lines because by drawing a line, you're saying every point between there, all the fractions, all the decimals, all the irrational numbers are all possibilities, but they're not possibilities here. Okay, next example. X plus 2 is greater than 0, and our domain is the real numbers. All right, domain is real numbers. We're used to that. But here we don't have an inequality like we're used to seeing because the x is not by itself. X plus 2 is greater than 0. Using our additive property of inequality, we can put this into a more straightforward format. So again, just like with an equation, we like to get our variables by themselves. How are we going to get this x by itself? Well, if it's x plus 2, the opposite of adding 2 is adding -2. And we do the same thing to both sides. And we'll get our new equation, x is greater than -2. X is greater than -2, and I got that by adding -2 to both sides, which my additive property of inequality says that I'm allowed to do. Add the same thing to both sides. And if we think about it, x is greater than -2. Well, -2 plus 2 is 0. So if x is -2 plus 2, that would get us 0. All right, so here we've simplified to x is greater than -2. Then we just graph it the way we would any other thing here. So a circle on that -2 and then a line going to the right forever. Notice it is a line here because we're talking about real numbers and not whole numbers or integers or anything else. Last example. X is less than 0, which normally wouldn't be hard to graph, except that we have to pay attention to our domain. And the domain here is not real numbers. It's not even integers. It's whole numbers. Whole numbers are the integers except for the negative ones. So negative integers are not an option. We just have 0, 1, 2, 3, 4, etc. Are any of those less than 0? No, they're not. Since we don't have any solutions here that are possible, we say that the solution is the null set. Oops. Or the empty set, whichever one you want to use. There are no solutions to this inequality given this domain. X is less than 0. Sure, there are plenty of solutions to that, but not if we're only restricting ourselves to whole numbers. So you can either write the crossed out 0 for the null set, meaning that there's no members of that set, or you can use the curly brackets with nothing in between, the empty set. Either way. So those are possibilities here. Keep in mind that when you're dealing with integers or whole numbers or whatever, you're not going to have lines. You're just going to have dots because we don't want to include all those values in between the whole numbers. Okay, that was lesson 64. It's a lesson number divisible by 4, so you should know that that means test coming up. We're going to have a test on Tuesday covering up to and including lesson 60. So stop by office hours. Do the homeworks, make sure you're checking your work, writing out your answers, writing out your work, that is, and your answers. And I look forward to hearing from you soon.